Hey there, chemists. In this lesson, we are going to look at the Heck reaction, named after Richard Heck. It's also called the Mizuroki-Heck reaction. It's a new way for us to make an alkene, or an olefin, and it comes from a palladium-catalyzed reaction that actually involves an alkene as the main reactant, and then some type of halide or triflate. If you're wondering what is a triflate, in case we haven't covered that, a triflate is a special type of leaving group. It's abbreviated OTF, and it's very similar to a tosylate in terms of it being a sulfate. It looks like that. Trifluoromethane sulfate is what it stands for. It's a great leaving group. Good LG. So it just involves an electron-poor carbon source, and the mechanism is what we're going to go through. So here we have an example of typically the carbon with the leaving group on it has to be sp2 hybridized, so you'll see things like vinyl and aryl halides, meaning aromatic. And typically, but not always, the alkene is usually attached to some electron withdrawing group, but we'll see some exceptions to that, so I'm not even going to write that just yet. But that's what the first example shows. So, when I take this vinyl halide and this unsaturated ester with palladium, I get a new carbon-carbon bond. I'll show you the product first, and we'll go through and explain the mechanism of how this happens. There's the product that we get. New alkene, new carbon-carbon bond right there. And the mechanism first involves what's called an oxidative addition between the halide and the palladium. This should be reminiscent of when we made organometallics in the past. We made organomagnesium reagents, Grignard's organocopper reagents, cuprates. This is an organopalladium reagent. This is an oxidative addition. So it turns that carbon into a nucleophilic carbon. It's much milder than the organometallics that we've seen in the past. So it actually doesn't react with esters in things like what we're about to show here. So then this organopalladium sees the ester, but it's the alkene. That's actually the reactive species here. And a new carbon-carbon bond forms between the more electron-rich carbon of the organopalladium and the more electron-poor carbon of the unsaturated ester. Remember, there's a significant resonance contributor in this ester that would look something like that. I could draw a partial positive charge on that carbon, and the organopalladium knows this. So I'm going to draw an arrow showing that carbon-carbon bond, and simultaneously another curved arrow where the pi bond forms a bond with the palladium. This is called an olefin insertion, or an alkene insertion, and it's simply because the alkene literally inserts itself in between the carbon and the palladium bond. It actually first forms a coordinate covalent bond with the palladium, but I'm just going to skip right to that. So what we get is our six-membered ring. We have a new carbon-carbon bond between there, and then the rest of this carbon chain that used to be the ester is along for the ride. And there's a new carbon-palladium bond right there, still attached. Now that olefin insertion occurs with syn stereochemistry. It turns out not to create multiple stereocenters in this one, but I'm going to show it anyway. This new carbon-palladium bond and this new carbon-carbon bond are syn relative to each other. So if I fill in what else is attached, we have two hydrogens on that carbon and one other hydrogen on that carbon. So how do we get to this product up above? Let's take a look at the intermediate where we're at, and how do we get to there? We have to lose this palladium species, and then we have to lose one of these hydrogens, which are effectively beta to the palladium. So they call this a beta hydride elimination. Now it can't do it as it's currently drawn. I need to redraw this and rotate around that carbon-carbon bond so that a palladium and the beta hydrogen are syn to each other. This will make sense when you see what I draw next. I'm going to rotate this. I'm going to keep the right half of the molecule the same and rotate that cyclohexenyl group so that one of the H's is now bold and in the same direction as the palladium. I'll actually just start by drawing that in. There's the H, and it's now syn to the palladium. What else is attached? Well, if this H is that in that spot there, that means the cyclohexenyl is now back there. There's actually multiple ways this particular one could rotate to give us a syn hydrogen. I'm going to show the one that's less sterically and cumbersome, and we'll see that that actually explains the trans-alkene product. But now we're set up to lose the palladium and lose the beta hydrogen, and this is in fact called a beta hydride elimination. Beta hydride elimination. And you can actually draw curved arrows for this. The hydride means the hydrogen and the two electrons that form its bond. So draw an arrow from the CH bond to the palladium. The palladium-carbon bond breaks, and those electrons become the pi bond, right back where it was in the very beginning. And that actually cyclizes up to give you that product. So there is a mechanism for the formation of that. You actually form a palladium with an HBr attached, and that palladium spits out HBr and regenerates palladium-0, which is actually what we started with in the very beginning. We have palladium-0. This palladium acetate species becomes palladium-0. I'm not going to go into that detail, but it's true. So you are catalytic in a palladium-0 source. The HBr is soaked up by the triethylamine base. That's just what happens with all those byproducts, the inorganic things. So that's the Heck reaction. Let's look at some examples of this, and we'll see there's some interesting consequences as a result of this syn olefin insertion and this syn beta hydride elimination. Let me go back and actually write that. It is a syn beta hydride elimination and a syn olefin insertion. Okay, so let's look at some simple examples. Here we have just cyclohexene and iodobenzene. And I'm going to draw the intermediates that you would get. You would get an aryl palladium. And then that will see a cyclohexene. You'll form a bond between the carbon, and then the palladium and the other carbon. I'm just drawing them as dotted lines. This is just how I figure it out sometimes to show me where the new bonds are formed. So I will get a phenyl group attached to the cyclohexene ring and a new palladium. Now, remember that olefin insertion occurs with syn stereochemistry. So that palladium and that phenyl are on the same face. And there's nothing I can do about it because the starting alkene was cis and locked inside a ring. So now if I want to do a beta hydride elimination, let's see, where are the hydrogens that are beta to that carbon-palladium bond? Well, I have one down there, but that's anti to the palladium. So then I have two others up here, and one of them is syn. This is the same type of thinking I hope you recall from doing E2 reactions when we needed to have anti-periplanar geometry. Here we have to have a syn relationship between the H and the palladium. So I'm going to get a new alkene between those two carbons. I'm not even going to draw the arrows for it. I'm just going to show the product, because this question just asks us to figure out the product. But that means I actually get what looks like an alkene migration overall. Instead of, like our first example, the new aromatic ring, it doesn't get attached to one of the alkene carbons in the end. It's one away. But that's why, because of this syn olefin insertion and then a syn beta hydride elimination. So let's try another one. Here we have acyclic molecules. This might be simpler. I first find the halide. That's going to become the organopalladium species. So it will look like this 5-carbon chain as an organopalladium. And then if I imagine what that does when it sees my ester, this is the same ester as we had above. It should be worth noting that the palladium ends up going to the more electron-rich carbon of the alkene, it's this carbon attached to the palladium, which you can think of as being more electron rich, goes to the more electron poor. How can you remember that? Well, metals are not very electronegative, so this bond dipole looks like that. So you have sort of a partial positive on the palladium, and therefore a partial negative on the carbon, just like any organometallic for all the ones we've seen. So then I'm going to form a bond between that carbon and the more electron poor carbon of the unsaturated ester, and then the palladium and the other carbon. So I'm just showing intermediates so I can figure out what the product is. That means we have a new carbon group there with the ester attached. And then my palladium is temporarily on that carbon. And then to do a beta hydrogen elimination, I've got 2 hydrogens beta. Either one of them can be eliminated because I can freely rotate around this carbon-carbon bond if I need to. And here's why you typically get the trans alkene. It will rotate to give you the sterically more favored product. So we get that ester in the end. Okay, so those are some simple examples. Let's wrap up by looking at a more complicated example of this. They actually gave us the product and were asked to draw all the palladium-containing intermediates, and then we'll finish with one example of how to use this in a synthesis where we have to predict the product. So here is a Heck reaction. I have an aryl halide and an alkene in the same molecule. So this is an intramolecular Heck reaction. So let me first just redraw everything with the organopalladium attached to where it used to be just a halide. Everything else is just along for the ride. And then to do the olefin insertion, which carbon of the alkene gets attached to which carbon of the organopalladium species. We have 2 choices. We can either form a 5-membered ring, or we can form a 6-membered ring. For reasons I'm not going to go into just yet, when you have that competition, you go with actually the 5-membered ring. This is called a 5-exo cyclization as opposed to a 6-endo. So I form a bond between those 2 carbons and those 2 carbons. Actually, I didn't need to rationalize it. I remembered they showed us the product, and we're just trying to explain what we get. And indeed, we get the 5-membered ring. So now I actually have a tricyclic species. Still have this ester. It's attached to an asymmetric carbon right there. And now where is this palladium? Well, this palladium is here. What's the relative stereochemistry? Well, those 2 bonds have to be syn to each other. And let's go one step further and try and imagine where those bonds are in this molecule that already has an asymmetric carbon. That ester is sticking straight up out of the page the way we've drawn it. It's been that way since the beginning. So I'm going to imagine this benzyl group with an organopalladium attached to it has to come from underneath that cyclohexenol ring as it's drawn. So those bonds are actually dashed lines, and I'm going to indicate that by just drawing bold lines for the hydrogens. Those hydrogens got pushed up as a result. Let me say that again. This stereocenter right here with that ester pointing straight up means this benzyl group is in the back. It's got to swing around underneath that ring and insert that alkene from behind the screen as you're looking at it right now. So that new carbon-carbon bond and that carbon-palladium bond are effectively dashed lines. Alternatively, you could draw those H's coming out of the screen, which means that this palladium and this beta hydrogen are not eliminatable. I have to remove a hydrogen that's beta and going in the opposite direction. So I'll draw in the other beta position. Perhaps it's clearer if we actually show those bonds with a little bit of direction. You can always show both directions and it's even clearer. So the palladium will leave. It still has a bromine on it, doesn't it? And this beta hydrogen will leave. So your product, indeed, is exactly what we see right up above. New 5-membered ring. New alkene out here, migrated from where it was earlier. I have this aromatic ring that's been along for the ride, and then actually a new stereocenter set relative to that existing one. So those palladium intermediates explained the formation of this product. Okay, let's wrap up and just look at a quick fill-in-the-blank synthesis, combining some old chemistry with some new chemistry. Here we have LDA. This will enolize that alpha proton. We learned this back in the enolates unit, so this is enolate alkylation. I could imagine drawing an enolate on the alpha carbon. It will do an SN2. So I'll have this 4-carbon chain attached to my 6-membered ring. 1, 2, 3, 4. Looks like there's an alkene on the end. LAH, reduction of the ketone. You'll turn that into a secondary alcohol. The rest of it's along for the ride. I'm not showing stereochemistry here. We'll just get a mixture of stereoisomers, I predict in this case. PBr3 will convert that alcohol into a bromide. And then here's the new reaction. We're going to try to do a HEC. And I actually want us to predict the product. So down below, I'm going to show what I predict the palladium-containing intermediates will look like. So let's first draw just the organopalladium. Interesting example where they're predicting an sp3, organopalladium. And then we're going to do a cyclization where this alkene inserts between the palladium-carbon bond. So that carbon right there is going to connect to either of those 2 carbons on the end. We said earlier in the competition between 5 and 6, we're going to predict a 5-membered ring. So I'm going to form a bond between that carbon and that carbon, the closer one, and then the palladium will form a bond with that distal carbon all the way on the end. So I end up getting a, let's go ahead and number, 1, 2, 3, 4, 5-membered ring fused to our existing 6-membered ring. Now where is the palladium? Well, let's number our carbons. 1, 2, 3, 4, and 5. 5 has another carbon attached to it sticking out of the ring right there, and that's where our palladium is attached. So then this will have to undergo a beta hydride elimination. There's only one beta hydride spot. It's on what's currently labeled as carbon 5. So you're going to lose the palladium, and you're going to lose that beta H, and you'll get an alkene right in between. So an exocyclic methylene is what I predict that we will get. So I'll have a 6-membered ring that I've had since the beginning, fused to a 5-membered ring, and then an alkene sticking out of that ring. So there's an application that follows a couple of other old reactions. Okay, so this is a new reaction for us, makes alkenes with some stereoselective features of it. That's the HEC reaction.